Hello everyone and welcome to this class dedicated to the structure of crystalline solids. So it is part of the course Materials and Their Properties that is given by the Federal University of ABC, and I am Professor Mathilde Champeau. So why are we going to focus on crystalline solids? Let's remember our objective. Our objective is to make a correlation between the composition and the organization and the structure of the materials with their properties. So in the last classes, we focused on the description of the atoms and more specifically on electronic structure. Then we introduced the different kind of bondings that we will find in materials. So the primary bonding that are ionic, metallic, and covalent bonding, and also secondary bondings. And now we are going to see the organization of these atoms. So we are going to introduce crystalline solids and to describe the organization of the atoms into this structure, and we'll differentiate crystalline solids with non-crystalline solids, which are amorphous materials. So after that, we will be able to correlate some structure with this crystalline, some properties with these crystalline structures. So first of all, we are going to know the difference between crystalline and amorphous materials in terms of atomic arrangements. Then we will introduce the concept of unit cell and be able to identify it. After that, we will focus on the first class of materials of this course. That will be metals, and we will introduce the three common crystal structures found in metals, and we'll identify important characteristics, and we will show a specific relationship between one property, which is the density, with the crystalline structure. And we will understand what is a monocrystalline and polycrystalline material. So we are going to see that physical properties of materials depend on the geometry of crystals. So the question we need to answer is, how do atoms assemble into solid structures? And we are going to give a specific focus today on metals, and how some of properties depend on this structure, and we will illustrate the correlation between the structure and the density of a material, of a metal. And next class, we will answer, for example, this question: when do material properties vary with the sample orientation? Okay. So first of all, let's introduce the difference between crystalline and amorphous materials. So basically, according to the spatial distribution of atoms or molecules or ions, depending on the composition of the material, the solids can be classified into two types. And here is a very simple representation, 2D representation of a distribution of atoms. So you have the same chemical composition. Basically, these two materials are composed of silicon and oxygen. So you have two oxygen for one atom of silicon. But you can see that the spatial distribution is quite different. So on the left part, you have a very organized arrangement of these atoms, whereas in a repeating manner, whereas on the right part, the right representation, you have a more random organization of these atoms. You can find a pattern that is repeated. So we introduce the definition of crystalline and amorphous materials. So crystalline materials are composed of atoms or molecules or ions that are arranged in a periodic or repeating array over a large atomic distance. And in fact, if here we represented 2D representation of these atoms, of these materials, in fact, this arrangement occurred in the 3 dimension, as we are going to show. So this is a description of a crystalline material. It is, we have a periodic organization of the atoms along a large distance in these 3D dimensions. Whereas in the case of amorphous material, there is no long range order. So or we say amorphous or we say non-crystalline, but it is the same description. And in fact, in amorphous material, we can find a short range order, which means along 10 or 100 atoms, we can find a repeating pattern, but it is not the case in long range, in long distances. So here you have some photo or microscopic images of different kind of materials. So you can see on the left part you have quartz. So quartz, it is in fact this it corresponds to this arrangement of atom. It is composed of oxygen and silicon, and so you can see that this crystal have a specific shape that in fact correspond to the arrangement, the 3D arrangement of the atoms that we find in this crystal. So in fact, the shape of this kind of inorganic materials of inorganic crystal corresponds to the description of the unit cell we are going to introduce. So then we have a bismuth macrocrystal. So you can see very nice patterns in this bismuth monocrystal. Then we have copper aluminum alloy, which means we have 50% of copper and 50% of aluminum composing this material. And so we have a crystalline structure in this alloy, in this metal. Then we have diamond, so it is only composed of carbon. And as you can see, we have different particles. So it seems to be particles in this image. And in fact, it corresponds to different crystals. We are going to see how they are formed. Then we have aluminum, which is a ceramic. And also you can see we can distinguish different shapes right here, and each of these blocks correspond to a specific crystal. And then we have an example of a polymer, which is a polyethylene terephthalate, the one that we find in plastic bottle. And you can see these spheric shapes. So these spheric shapes correspond to crystals. And the purple part of this image corresponds to amorphous part of these polymers. So we introduce different kind of materials right here with different crystalline structures and shape of these crystals. And in fact, crystalline structure will be found in metals, many ceramics, and some polymers. So last time we introduced the energy bonding, and so we have a relationship between energy and crystal organization. So in amorphous material, as we saw, we have a random packing of the atoms, so we have a non-dense material, whereas in a crystalline material, the packing of the atom is ordered, and we have a dense material. And in fact, this has a direct relationship with the bonding energy. So let's start with the crystal material. So basically, we introduced last time what is the energy bonding and the interatomic distance between two atoms. And so in the crystal, the interatomic distance will be quite defined. So it is the one that corresponds to the lower energy for the bonding. So we have this interatomic distance for our two atoms, and the energy bonding is found as the energy dwell, so the minimal energy found on this graphic. And for the amorphous material, in fact, this interatomic distance, or the typical neighbor, the typical distance between two neighbors is not optimized. So it is not the same interatomic distance than in a crystal, because as you can see, we calculate the average of the distance between two atoms. And so the average of this distance is a little bit higher than the interatomic distance at equilibrium we find in crystal. And so, in fact, according to this graphic that represents the energy as a function of the interatomic distance, so the energy of this material is a little bit higher. So it does not correspond to the minimal of this curve, but it corresponds to the energy found at this average interatomic distance. Okay, so the energy of an amorphous material is higher than the energy of a dense and older crystal material. And so this will have some consequences when we will introduce materials properties. So now let's focus on crystal structure or crystalline structure. So crystal structure is the manner in which atoms or molecules or ions are spatially arranged. And in order to describe the crystal structure of our material, we will introduce the crystal lattice. So the crystal lattice is a set of atoms which are repeated in three-dimensional space with a given periodicity. So this is our crystal lattice, and we are going to describe the crystal structure of this crystal lattice. Okay, so to describe a crystal lattice, we are first going to consider the three Cartesian axes, so X, Y, Z, and we are going to describe the position of these atoms in the crystal lattice. So in that way, we are going to describe the crystal structure. Okay. To do so, first of all, we need to introduce the hard sphere model. So last time, when we presented the atom and the composition of an atom, we introduced a planetary model that represents the nucleus at the center, and then the different electronic orbital and the electrons that are around this nucleus and that evolve around this nucleus. And so then we saw some cases that we introduced chemical bonds, and we said that in fact our atoms are can be represented at atomic hard sphere. And so it's a case of an atomic bond composed of two atoms of different radii. So we are going to consider such kind of situation where each kind of element is represented as a hard sphere, a perfect sphere which is indivisible and that have a specific diameter that correspond in fact to the distance between the center of the atom, so the center of the nucleus of the atom, and the outermost orbital of this atom. Okay, so as you can see, we have two different atoms in this case, and each atom has a specific diameter that corresponds to the atomic radius. So in fact, all different atoms will be packed in the same way that we succeed to pack these balls. Okay, so we are going to talk about the hard sphere models. In that case, the orbital of these two atoms won't interfere and won't interspace. So Now let's introduce to the unit cell in order to be able to describe the crystalline structure. So the definition of the unit cell is that it is the smallest structural unit or building block that can describe the crystal structure. So let's see an example. So let's consider that we have this 3D arrangement, which is a regular arrangement, or we called it the crystal lattice, okay? And we need to describe this crystal lattice, and to do so, we will use the unit cell. So the repetition and the arrangement in this crystal structure can be described defining the smallest building block. And in that case, the smallest building block that will be able to describe this whole crystal lattice will be these 8 atoms that form a cube, and we have 1 atom at each corner of the cube. And you can see that repeating this building block and making a translation of this unit cell, we are able to describe the whole pattern of our crystal lattice, okay? So in fact, this unit cell will represent the symmetry of the crystal structure, and it will be the way that it will be the tool that we will use in order to describe the crystalline structure of this crystal lattice, okay? So we are going to work on the unit cell. So let's make an exercise and consider this 2D pattern. So we consider this 2D pattern, and we are going to look for the unit cell for this geometric pattern. So in another way, we are looking for the smallest unit that can be used to build the whole pattern by translation, okay? So what is the unit cell of this crystal lattice? So here, in fact, I can use different, and I can find a different unit cell for this crystal lattice that are represented right here. So either you have this way, this unit cell, or that unit cell, or that one, okay? And you can see that by translation, all of them are enabled to describe the whole pattern, okay, the whole geometric pattern. And if you have a look, all of these 3 possibilities are, all of these 3 unit cells are composed of 2 lozenges that fit in one, in this geometric shape, okay? So in fact, all of them are quite equal, and I can use either one or another to describe, as a unit cell, to describe my crystal structure. So now we are going to look in 3 dimensions, and we are going to work on real configurations that we find in materials. And in order to describe the unit cell, we are going to use this specific condition. So first of all, the unit cell is a parallelepiped. We are going to work with Cartesian coordinate system, X, Y, and Z. The origin of this Cartesian coordinate will be at one of the cell corner, and each X, Y, and Z axis will coincide with one of the parallelepiped edges. So basically, if I represent this unit cell, let's say that it is a unit cell of my material. So to describe this unit cell, I will use this parallelepiped. So as you can see, this parallelepiped has 6 faces, with 2 faces parallel. On this side, 2 of them are parallel and 2 of them are parallel. That's why we call it parallelepiped. And we use a Cartesian coordinate system. So as you can see, we have the X, Y and Z axis. And the origin corresponds and coincides with one of the parallelepiped edge. So on that way, we have this dimension of this parallelepiped. So one edge that coincides with X axis, the Y axis that coincides with this edge of the parallelepiped, and this other edge that coincides with the Z axis. And so to describe the unit cell or this parallelepiped, we are going to use 6 parameters called lattice parameters. We are going to describe the 3 edges, so the dimension of these 3 edges, which are A, B, and C. So A along the X axis, the B along the Y axis, and the C along the Z axis. And we are also going to use 3 angles. So there are interaction angles. We have alpha, beta, and theta in order to describe these 3 angles. And in fact, we will find 7 crystal systems, which mean 7 unit cell geometries. So we have the cubic one, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. So we have 7 unit cell geometries. And the one that will be more important for the class, in fact, will be the cubic one and the hexagonal one. So in the cubic one, as you can see, the 3 edges have the same dimension, which is A, and A, because it is a cubic geometry. And the interaction angles will be equal to 90 degrees. In the case of hexagonal, the edges A and B will have the same dimension, whereas it will be different from the C axis, the C edge. Alpha and B will be equal to 90 degrees, whereas the other angle will be equal to 120 degrees. So, thanks to these 7 unit cell geometries, we are able to describe the different atomic arrangements that we find in crystal structure in materials. And after having described the 7 unit cell geometries or 7 crystal systems, Auguste Bravais in the 19th century wondered how many different ways can I put atoms into these 7 crystal systems and get distinguishable atom environments. So in fact, yes, you can consider one crystal system, and maybe there are different ways of filling these crystal systems with atoms. Okay, so let's take the example of the cubic crystal system that will be part of the focus of this class. So the cubic crystal system, as we described, have some specificity. So A equal B equals C, and the 3 angles are equal to 90 degrees. And so, in fact, Auguste Bravais showed that we have 3 possibilities to place atoms, to put atoms in this crystal system. Either we can place the atoms only at the edge of this cubic system. So it is represented right here. We will call it simple cubic system. Either he found that we can place atoms at the edge of this cube and 1 atom at the center of this cube. And so it described another crystal structure, which is called the body center cubic. Or either you can place 8 atoms at the corner of this cube and place 1 atom at the center of each face. Okay, so the atoms that are placed at the center of these faces are in purple, as you can see. So it is called the face center cubic. So it is a description and an example of how we can put atoms in these cubic crystal systems. But in fact, Auguste Bravet shows this description, amplifies this description for the 7 crystal systems. And so, as you can see, we already described the different possibility for the cubic system. But here you have all the description for the tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic systems. And so, in fact, Auguste Bravet proved that there is 14 distinct ways to arrange atoms in space. And so we are talking about the 14 Bravet lattice, okay? Lattices, sorry. And so in that way, we have all the possibility, or all the crystal structure or the unit cell found in crystal structure, we find in materials. So 14 possibilities. So why it is so important to focus on the unit cell? So we show that it is the smallest building block of the crystal that we find in our material. But in fact, by studying only the unit cell, we can get information about the whole crystal. So we are simplifying our study and our problem and getting the necessary information to describe our whole crystal. And so, for example, from the unit cell, we can find the distances between nearest atoms to calculate the forces holding the lattice together or the energy bonding. And we can also look at the fraction of the unit cell volume that is filled by atoms and relate so the density of the unit cell of our material to this atomic arrangement. Okay, so it is some example to show why it is only necessary to focus on the unit cell, or for that level of explanation of material property, we can only focus to the unit cell. So there are some important characteristics to describe the unit cell. So first, the number of atoms that is associated to each unit cell is an important characteristic, and we represent it by n. There is a coordination number, which describes the number of neighbor atoms in the 3-dimensional lattice, Cn. We have also the relationship between the atomic radius and the age, A. The atomic packing factor, APF. So we are going to define what is the atomic packing factor, and the volume of the cell as a function of the radius of this atom. So now let's focus on metals and their crystalline structure, since they are the first class of materials that we are going to study, because they present simpler crystalline structure. And so that's why we are going to focus first on this kind of materials. And you will see that several concepts that will be presented for metals will be applied to other crystalline materials. So let's remember that in metals, we find metallic bonding. And so these metallic bonds are non-directional, and they are formed by, or we can describe metals as composed by ion cores that in fact are composed of the nucleus of the atom and the non-valence electrons. And so between these ion cores, we find the free electrons so all the cloud of electrons that are composed of valence electrons that are free to move between these ion cores. And so the fact that we have this metallic bond non-directional make that we have no restrictions for the number and position of nearest neighbor atoms. So this enables to have a large number of nearest neighbors, or in other way we will say that we have high coordination number in metals. And the other aspect is that we have a dense atomic packing, or in another way to say that is that we have a high atomic packing factor, APF. And so when we will represent and when we will use a hard sphere model, we will consider that each sphere corresponds to an ion core. Okay. So the metallic crystalline structure that we will find will be basically three forms, because most of the metals crystallize into three forms of crystal systems that are the face-centered cubic structure, FCC, the body-centered cubic structure, BCC, and the hexagonal close-packed structure, HCP. And in fact, we won't find so much the simple cubic system. Only polonium crystallized in this simple cubic system, because in fact this system is so rare because the packing atoms in this way does not lead to a very high packing density. So this is the reason why the simple cubic system is not common in metals. So that's why we will not talk about this simple cubic system, and only about these three the two cubic structure, the face-centered and body-centered, and the hexagonal close-packed structure. So let's focus first of all on the face-centered cubic structure. So as you can see, the face-centered cubic structure, or FCC, can be described in the following way. So we have one atom located at each corner and one atom placed in the center of all the cube faces. So I can show you right here. So one atom located at each corner and one at the center of each face. And so either I can represent my unit cell using the hard sphere model. Sometimes it is easier to visualize my unit cell using a reduced sphere model. So you can see that each sphere is represented in a smaller sphere, in order to see in all the unit cell where the atoms are placed. And if I represent my crystal lattice, I will represent in this way as an aggregate of atoms. And so, as we said, the unit cell can be translated and is reproduced along the 3D crystal lattice. So this face-centered cubic structure is found in iron, the alpha phase of iron, copper, aluminum, gold, and so on. And so the exercise to describe this unit cell and the way to characterize this unit cell is to answer the following question. So what is the number of atoms per unit cell? What is the relationship between the edge length A and the atomic radius R? What is the coordination number? And what is the atomic packing factor? So these four parameters, you should be able to find it or calculate it, but we are going to do it together. So what is the number of atoms in the unit cell? So basically, we can count the number of atoms that are placed at each corner. So we can see that we have 8 atoms that are in such equivalent position. And in fact, these atoms are shared by 8 unit cells. We are going to see it in a more later. And we have these atoms that are located at the centers of all the cube faces, and each of them are shared between 2 unit cells. So when one atom is shared by 2 unit cells, we should consider that we have half an atom in the specific unit cell. Okay, so basically, I will count that I have 6 atoms that are shared by 2 unit cells divided by these 2 unit cells. Okay, so we have 6 atoms that are placed at the center of each cube face, equivalent to this red atom. And in the same way, the atoms that are placed at the corner, equivalent to that one, that blue one, are divided by 8 unit cells. So I calculate 8 atoms divided by 8 unit cells plus 6 atoms at the center of each face divided by 2 unit cells. So in total, I have 4 atoms in the unit cell of a FCC structure. Second question, what is the relationship between the edge length A and the atomic radius R? So the first question that you should ask is, in which direction do the atoms touch one another? And so looking to this structure, you can see that along the diagonal of one face, you have these atoms, these 3 atoms that touch together. So across a face diagonal, I have the length of this diagonal, which is equal to 4 r cubic. That is equal to the length of this edge, a cubic, plus the length of this edge, which is equal to a cubic. So if I solve this equation, I have my relationship between a, the length a, and the atomic radius r. So then what is the coordination number? So let's remember that the coordination number, it is the number of closest atoms for one specific atom, so the number of closest neighbors. So let's consider these specific atoms right here. So as you can see, in this unit cell, specific unit cell represented in blue, it has 3 neighbors atoms that are positioned on at the center of these faces. Okay, 3 of them. Considering this unit cell, we have also these 3 atoms. Okay, but one of them was already counted on the previous unit cell. This one, that one, that one, that one, that one, that one. So totally, we can count 12 closest neighbors, okay, in the way that we counted in each unit cell, okay? So in that way, the coordination number in the FCC structure is 12. Now let's calculate the atomic packing factor. So what is the definition of the atomic packing factor? So this is very important in this lesson. So it is a fraction of the volume of the unit cell that is occupied by atoms. So how do we calculate the atomic packing factor? So we will calculate the ratio between the volume of atoms in the unit cell and the volume of the unit cell. So the volume of atoms in the unit cell, we will write it VA. So the volume of atom in the unit cell is basically the number of atoms in the unit cell times the volume of one atom. So an atom is considered to be a hard sphere of radius r. So basically I have 4 atoms times the volume of one atom. And then to calculate the volume of the unit cell, so I should calculate the volume of a cube. I can express it either with the length A, either using the radius R. So using the relationship we calculated previously. So the atomic packing factor, if you simplify the equation, you will obtain that the atomic packing factor is equal to 0.74. So this means that 74% of the unit cell is occupied by atoms. So it gives an idea of the density of the unit cell. And since we said that the properties of the unit cell are reflecting some properties of the wool crystal and of the wool material in the case of metals, so that means that the density of this metal, or yes, of this metal is quite high, because as we will compare with other kind of structure, this atomic packing factor is the highest that we can find in a unit cell, and so for metals. So now let's focus on body-centered cubic structure. So how can we describe the BCC crystal structure? So in fact, we have atoms located at each corner of the unit cell. So 8 atoms placed at 8 corners of the unit cell. And we have a single atom at the cube center. So represent it right here, or this sphere when I use a hard sphere model. So this kind of crystal structure is found, for example, in chromium, iron, tungsten, and so on. So doing the same exercise, we will calculate the number of atoms per unit cell, the relationship between edge length and atomic radius, the coordination number, and the atomic packing factor. So basically, since this structure is more simple than the FCC structure, so you can do the calculation, and you will find that the number of atoms per unit cell is equal to 2, because we have 8 atoms placed at the corner divided by 8 unit cells, and you have 1 full atom at the center of the unit cell. So basically 2 atoms per unit cell. Then to calculate the relationship between edge length A and the atomic radius R, you should consider that in this structure, the atom touches each other along the cube diagonals. And so in that direction, you will have the atoms that will touch each other. Okay, we say that they touch each other because it is the most compact. It is the most compact way to put this atom in the unit cell. And so in that way, the direction where the atoms touch each other in the ways that have been compacted in the unit cell are along the cube diagonal. And so in that way, you can make the calculation and the relationship between the length of this diagonal, which is equal to 4 radius of the atom, because you have 1 full sphere. So the diameter of this sphere along this direction is equal to 2 times the radius, and each atom at the corner participate to this unit cell and along this direction by its radius. So 2 times this radius and the diameter of the atom at the center of the structure. So you have 4 times the radius along this cube diagonal, and then you can calculate this relationship. Then let's see what is a coordination number. So the number, the number of closest neighbors. Sorry. So the number of closest neighbor, in that case, it's quite obvious. You should consider the atom placed at the center of the cube. And so its closest neighbors are the atoms placed at each corners of this cube. Okay, and for the atomic packing factor, so knowing the relationship between A and R in this structure, you can calculate using the formula given above. And you will find that the atomic packing factor in the BCC crystal structure is equal to 0.68. So it is lower than the atomic packing factor found in the FCC structure. So which means that in fact, the materials that will crystallize in FCC structure will be denser, more dense than the ones that will crystallize in a BCC crystal structure. And we know it calculating the atomic packing factor of the unit cell. Finally, let's have a look to the hexagonal closed packed crystal structure. So this structure is a little bit more complicated. It is found in cadmium, in cobalt, zinc, and so on. And in this structure, we have on the top and bottom faces of this structure, we have 6 atoms that form an hexagonal and that surround a single atom in the center of these hexagons. So these describe these 2 faces. And in the middle of this hexagonal structure, we have in this plane 3 atoms. So if we have a look, in fact, we have 2 kinds of planes. We have the A sides, or top layer and bottom layer, and the B sides that are positioned in the middle layer. And so, as you can see, if you have a look on the top of this structure, so you will have a superposition of the top layer and the bottom layer. This atom will superpose, and whereas the middle layer will be positioned in that way. Okay, so the center of this atom of the middle layer will correspond to the center made by these 3 atoms that are of the top layer or bottom layer. Or in another way, I can consider that I placed the atom in the A layer, so A compact plane formed by rigid sphere. And we have 2 kinds of interstices, which are marked as B and C in this graphic. And the second plane, the middle plane, is formed by placing the rigid sphere B on the interstices B. Okay, and then the third layer, which is the top layer, composed by the spheres A, are placed in the interstices of this B plane or middle plane, and superposed to the atom of the first layer. Okay, so in that way we have a very packed structure, as we will see by calculating the atomic packing factor. And so once we describe the hexagonal closed packed crystal structure, we can answer this question: what is the coordination number of atoms per unit cells, and so on. So let's start with the coordination number. So the coordination number is quite easy to calculate and to visualize, considering the atom that is placed at the center of the top layer. Okay, so at the center of the hexagonal. So this green atom has 3 close neighbor, considering the top layer, another top layer, so as another unit cell. So these 3 atoms are placed in the center of the next unit cell, the unit cell placed above, and it has 3 close neighbor within the unit cell. Okay, that is represented right here. So apart from these 3 plus 3 atoms that are at the center of a unit cell, it has also these 6 close neighbor that forms this hexagonal plane. Okay, so 3 at the bottom, 3 at the top, and 6 in the same plane. So it has 12 closest neighbors. Okay, so then second question, what is the number of atoms per unit cell? So in that way, considering the unit cell represented right here, we have 3 full atoms that are placed at the center, so in the middle plane, okay, that composes this unit cell, and they are totally within the unit cell, so 3 full atoms. Then we have totally 12 atoms that are placed at the corner, and if you have a look, they are shared with they are shared by 6 unit cells totally. Okay, so I count 12 atoms at the corner divided by 6 unit cells, and I should consider also these atoms that are placed at the center of these hexagons, top and bottom planes, that are shared by 2 unit cells, that one that is represented and the other one at the top. And so totally we calculate that the number of atoms per unit cell is equal to 6 atoms. Then to calculate the relationship between edge length A and atomic radius R, and the relationship between edge length A and edge length C, sorry, I made a mistake. So in fact, it's very easy to calculate the relationship between A and R, because in fact, along this corner, the 2 atoms touch each other in the first layer, in the bottom layer, they are packed together, and along the corner of the hexagon, we have 2 atoms that touch each other. So the edge length A is equal to 2 times the radius of the atom. Then, considering that the structure is highly packed, we can also calculate, if you want, there is a nice demonstration on this link, so you can understand why the relationship between C and A is C, which is equal to 1.63 times A. Okay, so to have a closed structure, we have such relationship between C and A. And finally, the atomic packing factor is calculated first by calculating the volume of atoms in the unit cell, which is 6 times the volume of a sphere, because we have 6 atoms in the unit cell. And so by using this relationship between A and the atomic radius, we can also write the volume of atoms in the unit cell using the parameter A in such a way. And the volume of the unit cell is equal to 6 times the area of a triangle, as shown right here. So the hexagonal is composed of 6 triangles. Considering the volume, we should multiply it by the height of the unit cell, which is equal to C. Okay, so in that way, we can calculate the atomic packing factor, which is also equal to 0.74, which means that as in the FCC crystal structure, 74% of the unit cell is occupied by atoms. So it is also a very dense unit cell. That's why we say it is a close packed structure. So here in this table, you can find various metals and their crystal structure and atomic radius. And as you can see, for example, considering gold and iron, so they have different atomic radius and they are packed in different crystal structure. And so in that way, the gold, which is crystallized in FCC structure, is more dense than the iron, considering the mass of the atom, but also considering the crystal structure, which is more dense in the case of FCC, so more dense in the case of gold than in the case of iron. Okay, so you can see the relationship, or at least the crystal structure in which each metal crystallizes. And so we have an idea, as we said, of the density of the metals. So to calculate the density, in fact, we should use this equation. So this equation gives a relationship between the number of atoms in the unit cell, the atomic weight, the volume of the unit cell, and the Avogadro number. And so not only we should consider the unit cell, which is directly related, or from which we calculate the number of atoms per unit cell and the volume of the unit cell, but also we consider, as we said in the previous example, the atomic weight and also this Avogadro number. And so in that way, we can calculate the density of the metal. Finally, to finalize this class, so we are going to talk about polymorphism and allotropy. So what is polymorphism? It is a phenomena by which a solid, which can be metallic or non-metallic, can have more than one crystal structure depending on temperature and pressure. So in the case of silica, we have already presented that silica can be crystalline or amorphous, but in fact, it can crystallize in different crystalline structure. So as you can see, they are very different from A to D. The atoms are organized in different way. So the A1 corresponds to quartz, the D1 corresponds to cristobalite, and the kind of unit cells that we will encounter for silica, which has the same chemical composition but different crystalline structure, will depend on the condition to which this material is submitted, okay, temperature and pressure. And from the polymorphism, we can define allotropy, which is the polymorphism applied in case of a pure solid composed of only one element. So for example, you know that diamond and graphite are made up of carbon atoms, only carbon. But since carbon atoms can be arranged in different crystalline structure, it can form either a crystalline structure that takes advantage, or that is based on the hybridization of carbon in sp3 that we described in the previous class. In that case, it's create a diamond, it's formed diamond, or carbon is hybridized in sp2, and in that case, it creates graphite. So this diamond is created at a high temperature. And so as you know, it is the same composition, but the crystalline structure will make this material to be much more expensive if it turns to be the crystalline structure of diamond compared to in comparison to graphite, which is not so, which do not have such a high commercial value. Okay, so in that way, considering this example of carbons that can crystallize either in to form diamond or graphite, we introduced allotropy. So another example presented in this table of allotropy is for these three metals. Depending on the condition, they form one structure or another. So you have some example. At room temperature, you have such crystal structure. For example, for cobalt, so it forms the hexagonal close-packed crystal structure. And above a certain temperature, in this case 427 degrees C, it forms, it transforms into another crystalline structure, which is a FCC structure. So finally, let's define monocrystalline and polycrystalline materials. So a monocrystalline material is constituted by a unique crystal through the entirety of the specimen, okay, of your sample, without interruption. So all unit cells will have the same orientation because they are repeated in the same way along the three directions of the material, okay? Whereas a polycrystalline material is constituted by many crystals, or what we will call grains, and each one with a respective spatial orientation, okay? Which means that, for example, in this image, you can see that we have different part of this material, which is alumina. So each part has the same composition, but in fact, each block corresponds to one grain or one crystal. And in this crystal, we have many unit cells that have one specific orientation, okay? All of the unit cells are built along one orientation. And in the next block that you can see, we have another set of unit cells in this crystal, but that have a different orientation. So if the first one has one orientation in that way, so we have the construction of the unit cell translation along this direction, in the second one, we will have a different direction, okay? So this alumina, for example, we will say that it is polycrystalline, and visually we see this as different grains, okay? Different blocks that we call grains. And the last definition right here is the grain boundary, or contornos de grão in Portuguese, which is a region that separates crystals of different orientation in a polycrystalline material. So in this alumina sample, the grain boundary will be these dark lines that in fact separate these grains, okay? And in this case of the polyethylene monocrystal, in fact, all this part around this parallelepiped is, I think it is amorphous. And here we have one unique crystal, okay? So this crystal, I mean, it is a monocrystal of polyethylene, okay? Through this entire specimen, we have one monocrystal. So when the grains exhibit preferential crystallographic orientation in the material, as we will see in next classes, we will say that it has a texture. So we will introduce this concept again later. So how do these crystals in different crystals with different orientation are created? So first of all, it begins by a phenomenon, physical phenomenon, that should provoke the creation of the first unit cell. So in the case of metal, generally, we should consider that during the processing of metal, we will melt the metal and then we will cool the metal in a controlled way by decreasing the temperature of the liquefied metal. And so during this process, we will observe that the first atom that will organize, okay, will create the first unit cell. So the unit cell right here is represented as a cube, okay? And this unit cell, some atoms will diffuse to this unit cell and create a second unit cell, okay? A neighbor unit cell. And so this first unit cell, we call it the crystalline nuclei, okay? And then with the diffusion of these atoms to this unit cell, this first crystalline nuclei, we have the growth of the crystallites by the addition of these atoms. So these crystallites will continue to grow. These crystals, or what we call crystallites, will continue to grow up to solidification. So they cannot grow anymore. The atoms are involved in these crystals. And if we look at the microscope, how do this, what is the aspect or the visual characteristics of all these crystallites that has grown in different directions? As you can see, the orientation is different. They has grown in different directions. So in fact, we will see such kind of image of, or exactly what we presented in the case of alumina. We will see different grains separated by grain boundaries, okay? So maybe in the way we described how each grain has grown from the creation of a unit cell up to the final solidification and the final shape of each of these grain, you can understand better what we call grain, what we call unit cell orientation, and so on. Okay, and so we can observe this grain boundary using a microscope. So a crystallite, the definition of a crystallite will be a set of unit cells. So we have the unit cells, and when the second and the next close by unit cell will be created around the first unit cell, so we will call this this package of unit cells crystallites. So the grain, the definition of a grain is a structural arrangement ordered in crystalline materials formed by the growth of the crystallites. So at the end of this class, you know the difference between crystalline and amorphous materials in terms of atomic arrangement. You know the concept of unit cell, and you know how to identify it, to describe its geometry with its lattice parameters. We saw the three common crystal structures found in metals, and we identified the important characteristics. So of the FCC, BCC, and HCP. And also we presented the definition of monocrystalline and polycrystalline materials. We introduced what is polymorphism and allotropy. And we also introduced how the grains are formed. And we made the relationship between the concept of unit cell and the concept of grains in a crystalline materials. Okay, so thank you very much. If you have any question, you can send me an email, and I hope that you have learned a lot about crystalline structure in metals. And so next time, in the next lesson, we will continue to describe the crystalline structure in material, introducing new tools. Thank you very much.